All right. So today's an exciting day. Um, we've talked a lot about binary classification learning models, right? To go all the way back to the beginning of the course, where we had this example of building an AI model to figure out if we're looking at a cloud or not, where we feed in the image and it processes all this data. And then finally, at the end of the day, we get a number between 0 or 1. That's the AI's, our learning models, probability of this either being a cloud or not a cloud, right? 0 or 1. Like Rachel was saying the other day, like those are the two possible label values, and we want to see how close our model gets. Today, we're going to learn about multi-classification models, where maybe we want our image classifier to not just be able to tell me, is this a cloud or not a cloud, but what kind of picture it is. It could be a tree, it could be a cat, it could even be a picture of a cat in a tree. And we'll talk about why that's a particular distinction that matters in just a minute. And the cool thing is we're not going to have to make drastic changes to everything that we've learned to do this. Um, give me one moment here, folks. Let me move Slack off of my screen share screen just in case I need it for anything. And actually, as long as I'm doing that, we might as well do our tiling. So today we're going to talk about multi-classification, right? And it could not just be for images, it could also be for something like weather. Is it going to be sunny or rainy or cloudy? The example we're going to talk about is going to look at student grades. And we might even, as an assignment, look at a data set that deals with classifying like stars, some astronomy data. So we're going to do a little bit of review just of the binary models that we know and love. I'm going to talk about the different kinds of multi-classification models briefly. Very briefly introduce a new activation function called Softmax that we'll be using. We'll go through the pre-processing for multi-classification, and there's one key thing we have to do differently that I'll talk about. We have to have our label data be a different data type. It needs to be an integer or a long, not a float. We're going to use a different loss function, and then we'll see we have to make one tweak in our evaluation code. Do folks have any questions about the agenda for today's lesson? Okay, cool. Let's dive on in. Let me go ahead and let's just hop over here and let me just pull up the binary model that we know and love just so we can see it. And give me one sec. Pull it in here because I'm going to paste this in just one go, I think. Here we are. So here's the binary model we've come to know and love. And let me go ahead and import an N. Or can anyone remind me, how do I import the neural net module? Well, I believe I do from torch import an N, right? Because it's coming from there. Sorry about that. And we've got here our binary model that we've seen. Um, we have our linear layers, right? This is the one where we start with 9 and we go to 18. Someone remind me what is NN dot dropout doing here on line 7, line 9, line 11?
Early stopping, if the range is going, like if the training model isn't training in the direction that we want to.
Um, Close. We did talk about early stopping. Dropout is actually something else.
Isn't that when it like removes one of the I can't remember the word for it, but
Oh,
removes
a
like one of like the
neuron.
neurons or whatever?
Yeah, exactly. Exactly. Like somewhere around here, if I scroll through all of our various diagrams, we should have, there we go. Yeah. That was a great description of early stopping, though, Jack. That's just something else. And so
Gotcha.
dropout, yeah, dropout, remember, is for each layer during training, not during evaluation. Um, a certain percentage of neurons will randomly just get ignored and not used. And this includes our input layer, which is kind of weird and confusing because it's like, don't I want all the data? Well, as we saw last week, we actually got better performance when we do have dropouts in the input layer than when we don't, because maybe our learning model, um, for some reason, over relies on, trihalomethane data, and dropping out that kind of data forces the model to do a better job of using all the other information it has. And can someone remind me, like, how many neurons in each layer get dropped out?
It's just one, isn't it?
It is not just one. Um,
Isn't it random?
it is random. What does this P equals 0.5 here represent on line 7 when we're creating this dropout?
Is that a 5% chance that any individual neuron gets dropped?
Very close. It is a 50%
50.
chance that any individual neuron gets dropped. Yeah, yeah. We'll usually see probability values represented between 0 and 1. So you all are absolutely right that it's a random neuron that gets dropped. And I didn't mean to ask a trick question. The model doesn't, we're not necessarily guaranteed that exactly 50% of them will get dropped each time, right? Because it's just a probability. But we can set the probability that an individual neuron will get dropped. So if I do this, 100 times, then on average, half of my neurons will be dropped, right? So I think it's safe to say that with a probability of 50%, we're dropping half the neurons in each layer. To kind of go back to our big O discussion last week, it makes sense. We can think about sort of the most extreme, it's not worst case because it's not bad we're dropping neurons, but the most extreme scenario where the probability, the dice roll the right way every time, and we do indeed drop 50% of the neurons.
So on this binary model, so it linearly is it pretty much saying like, for example, line 7, it's pretty much casting a 50% chance that it's going to, like it's going to drop one of the 18 neurons and it goes one by one through each
Exactly.
18
Exactly.
neuron.
And if I change this, then specifically here in like layer 2, which is, I believe, like if this is layer 1, then this would be layer 2. You know, now I've changed my dropout probability to 20%. So one in 5, right? So there's a much lesser chance of a neuron being dropped here in layer 2 if I make this change.
I guess another thing that could happen though, what if, even though you say 50%, for instance, what if like say that the input neuron for the next layer ends up being lower than the output, for the following one? I mean, there's always a chance that that could happen.
Right. Well, and that will happen even regardless of the percentage I put in, right? If I you do let's see how many neurons we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think I stuck a tenth in there. Let's not worry about the percentages, but let's just drop some neurons here. Even if just one neuron get dropped, exactly like you're saying, Jason, we run into this problem where like, and let's just have one here to show the example. And let's just, let me do a little duplicating.
I mean, the odds would be low, but it could theoretically happen.
Yeah. Oh no, it definitely will happen. Um, I'm going to get rid of the arrows because they just kind of get in the way. And we 1, 2, 3, 4, 5, sorry, 6, 7, 8, and one more, 9. So let's say these yellow guys here are the input layer of this layer right here that happens right after our, or excuse me, the input neurons of this hidden layer right here that happens right after our input layer, where we've got 9 of these things feeding in. And, Jason, you're totally right. Because even if we only drop one neuron here for this input layer, and this is true for any layer, then all of a sudden, all these other neurons get one less data point, right? Because each neuron sends, it sends its data to all the other ones. So an input neuron is always going to get data, right? Unless we dropped every single one, because even one neuron will send its weights and biases, and its sort of outputs of that tensor onto the others. But exactly like you're saying, like this input neuron won't get as much, right? Because this one isn't feeding its data. PyTorch handles that for us. I don't know if it puts in a 0 value or duplicates the value. I'd have to double check, but it's in essence doing something so that doesn't break the input neurons, which I think is what you were wondering about, because
Yeah.
if I was understanding correctly.
Yes.
Yeah, which is a great point. Yeah, so the good news is PyTorch handles that for us gracefully. And so we can control the probability that any individual neuron will be dropped from any particular layer with this probability value here in the dropout setting. And then we've got our sigmoid function over here. If I scroll over a bit so we can see it in the diagram, and I'll maybe just squeeze this in a bit more so we have a bit more room, and I'll zoom out maybe just a touch. I wish there was sort of an intermediary like zoom setting. I tend to draw big. But so we've got the inputs, they go to the sigmoids and they hit the outputs. And can someone just remind me, what is this ReLU here doing again? What's ReLU?
Removes negatives, I believe.
Yeah, yeah, exactly. It's another activation function, right? That we're actually feeding the output of each of these layers into. And exactly like you were saying, what ReLU does is, let me kind of hop over to our little diagram that we have over here for it, and I'll just zoom in. There we go. ReLU. So ReLU will take negative values and just turn them into 0. So any outputs from an activation layer that we feed into ReLU, any negative values, ReLU will just turn into 0. and it can help the model learn faster because it sort of pushes us to get to a conclusion sooner because we need everything between 0 and 1 anyway. And so if these values are negative, we know they're not good. So let's just push them to 0, which is a little bit of hand wavy, but that's the essence of what it does. I am going to get rid of ReLU for multi-classification for today. Oh, I guess we can leave it in actually. My apologies. Yeah, I got confused because we're adding in the Softmax layer later on, but that doesn't mess around with ReLU. And again, where we're using ReLU is we can see right here one of these linear layers. We feed the output of it, whatever self.ly returns, into this ReLU function. And ReLU then does its tweaking of those values and they're passed on to the next layer, and ReLU does tweaking and it's passed on to the next layer into the sigmoid, and then we're done. And someone just remind me real quick, what does this forward method do? Like, why do we need it? And maybe a bit more interestingly, could I rename this to like my forward? Will that work?
Doesn't the forward method like basically make sure the values are passed forward between the layers?
Yeah. It's exactly what it does. And it actually executes the neural net doing something, right? Because here we're actually passing the data into layer 1 and into layer 2. And if we do dropouts and we get a value, and then we pass it into the next layer and so on. So this is where we actually use all these layers we've created, right? And this is a bit of a trick question, but can I, rename the forward layer to do the work?
I believe no, it has to be forward because that's the method that it's looking for to run it.
Yeah, exactly. Exactly. Um, and if we go look at the PyTorch module class real quick, we give it a second. We'll see that this is some polymorphism in action, in essence, that even in this example, they're using a forward method. And if I scroll down here a bit to, let's find where they define it. Here we go. So as it says here, this defines the computation, right? The actual doing of the work that should be done at every call. And it should be overridden by subclasses, right? Our binary model inherits from this module class. So the module class is the parent for our binary model class. It's the child class or subclass. And the way that the PyTorch people designed the module class is they're expecting us to override, to write our own version of forward, which is an example, in fact, of OOP polymorphism. And I just want to check in and see if folks have questions about forward or anything else that you might be curious about with this code for the binary model itself while we're kind of doing our review. Okay, awesome. Let's throw up a multi-classification model, and I'm just going to throw it in there. And we can look at the two side by side to look at their differences. And I want this to be marked down. And while I'm doing this, actually, I do have a question for you guys. Is like a learning model to figure out if uh, a comment is offensive or not. would that be maybe like a binary classification or a multi-classification model?
I would say multi.
I would say binary.
How
It's a
so?
binary. Yeah.
I would say binary because it would be a situation that you would give it a certain, I'm assuming you would give it a certain input of words, and it would just essentially be matching there unless you're trying to go for like the in-between words that are that people make like in gamer tags where they put in offensive words in the middle of other words.
And that's why I said multi, because you have to like categorize each, comment or whatever as good, bad, in between, and so on and so forth.
I mean, I guess I would say if you're only presented two choices, true or false, then it's just binary. It's just that straightforward.
Right. And I actually think I think the answer here could be it depends, but you guys touch on a couple really good things that I want to hit on. And so let me kind of go through what people said one by one because you guys touch on a lot of good points. So binary versus multi-classification. Let's talk about similarities and differences. So similarities, both models take multiple features as inputs, right? So for both models, I could have, with my pH hardness of 0 point, like water data. Oh, I can't do a Python comment here. This is killing me. 0, 5.4, 3.3, 2.1, so on. And like we wouldn't actually feed a whole sentence like this in, probably. It might be broken up into something. This is not really how natural language processing works, but it might look like this. Let's have it be like one is a list of noun verbs. And the other is a list of nouns. And they isn't really a noun, so we'll not put that in there. And again, I'm sort of making this up, but it does show how we can think about the sentences in a structured way, right? And so the number of features, and if I was understanding Kenny, and I think a couple other folks were touching on this, it doesn't matter if we are looking at like one feature, two features, three features, both models can take a whole bunch of different kinds of data as input. The difference is really in the output. And the Jupyter notebook really got away from me there. I keep hitting Shift Enter because I think that's what I have to do, but it's not. And so for binary models, there's two possible labels. And Rachel was saying this the other day. 0 is false, 1 is true. Cloud or not cloud. And the model outputs a single value between 0 and 1. That's the probability of the thing, of the picture being a cloud. And I know you all know this. I think also just, when we talk about it in a new context, it's useful to review it again. So, right, 0.7 means like 70% chance the picture is a cloud according to our model. For multi-classification models, we have multiple outputs. So a binary model like outputs one number. Right, representing a probability. But for a multi-classification model, sorry, it's such a habit because I'm just so used to hitting Shift Enter in Slack when I'm adding code blocks. So Slack doesn't send the comment. We could have a cloud, we could have a tree, we could have a cat. And so we would have multiple outputs that would look something like this. And we should really say here probability. Right? There's 3 different classes our image could belong to. And the model will give us a list essentially with 3 different values, with 3 different numbers. So to go back to this offensive comment question, I didn't mean it as a trick question, but I really think the answer is both, right? Because as a binary model, we get true or false if the comment is offensive. As a multi-classification model, we could get, the kind of offensive comment it is, right? If it's, I don't know, let's say the categories are all the terrible things of the internet.
Different languages,
Say that again.
offensive words in different languages.
That is a good thought. I think that introduces too many complications because we would have had to like translate everything. Essentially, the issue of different languages would have been dealt with before the data even gets to our model. You know what I mean? Like if we had a comment that was in 3 different languages, we'd either send it to 3 different models, one for each language, or I don't know exactly how they would deal with it. But by the time it gets to the model, or the model is designed to be able to understand multiple languages, though I don't know if I know enough to know how good or bad an idea that would be. But point would being this the sort of language issue would get resolved, right? So that the model can understand everything, and then we just get back if it's offensive or not, or what kind of offensiveness it is. Does that make sense? Yeah, that's definitely a good thought about different languages. And that is an interesting question. That would be interesting to read up a bit on like how does that work? Like, how does sort of AI content moderation for multiple languages work? Do they make a model per language? I don't know. And I'm sure that is a real world problem that, Facebook or some company out there is dealing with. So again, I didn't mean this as a trick question, but this is why actually I think this is a really good discussion. This is probably the simpler thing to make, right? A binary model that says if a sentence is offensive or not. But I think you all have seen, what is it, on YouTube? If you want to report an offensive comment, you can like label like what kind of offensiveness the comment is. And so I'm pretty darn sure that there are real world models out there that do multi-classification for this kind of stuff because it's just it's very useful, right? Because you might have to deal with each of these in a different way. Like, for example, threatening language, maybe we need to notify the authorities. Though unfortunately the internet companies don't seem to have that sort of liability on their radars. But anyway, point being, like, we might need to take a very particular action for a certain kind of offensive comment. So being able to have like multiple classes or categories could be really useful. What are people curious about? What questions you'll have around this discussion, which I think is really good.
I mean, also language is like very contextual. So like how would we factor that into the language model to understand the context of like somebody could be right, like if a computer doesn't care if somebody's tweeting something or they are quoting somebody else's tweet, for example, or something like that, or whatever. Um, so like if somebody's just quoting like a Hitler quote, for example, right? They're not specifically saying that, they're just regurgitating his quote versus if somebody is quoting that themselves, how would a computer tell like what the difference is?
Yeah. The short answer is it can be tricky. I mean, I guess the really short answer is I don't know, but it can be tricky. Also, this stuff gets built up manually over time. Um, and and again, like it's trained on real world data, so you have like tens of thousands to millions of real conversations or things that people say. Um, to be used. So to use the sort of the classic, what's that joke? There's some internet rule like every conversation will eventually like devolve into a conversation about Hitler or something. Um, but just to use that extreme example, I'm pretty darn sure just at some point one of, the people on the team building this model would add that in and write some code and tell the model like, hey, if you see this, it means XYZ, or add like a 0.7 to your weight and bias for that thing or something. But also remember that the data is already categorized. So the model is probably going to be trained on, if we don't have tens of thousands of terrible sentences that like humans have looked over and categorized as offensive or not, we can't even train our model to begin with. And there's a huge amount of labor that goes into creating that training data. I think, in fact, a lot of third world labor. Um, and a story I heard, I don't know if you all remember, like when Google was offering like free phone calls, I think over the internet. They might still do it. They were doing it when I was in like college and stuff. And the story goes they were using it so that they could gather like actual conversation data. Um, but I don't know how much Google probably reads our email. They definitely see every single thing we search. But they've been hoovering up data for decades now, um, specifically for this kind of reason, to improve the search algorithm and stuff like that. I hope that helps answer your question, Chase. I realize I got a little into the weeds there. Yeah. So, and just to recap, because it's a really good question, how do we deal with the nuance of language? There's really three answers. One is in the training data, we need humans to be classifying like sentences and stuff already so that nuance is addressed. Another is there is a lot of research that's gone into natural language processing to do stuff like sentiment analysis and things like that. And the third is whenever you're training a model to do some sort of sentiment analysis stuff or NLP stuff in the real world, you've got people tweaking it anyway. There's I'm trying to think of a good example with the Google search. What's like something that would be what's something that would be confusing to search for that could have two meanings that is also work safe and appropriate?
I was thinking about this earlier because I'm a basketball fan. I was watching my Sixers play the other day, and they're just not good. So I commented, "My Sixers are cooked."
Yeah, that's a great example. And in fact, let's stick it into ChatGPT. I'm really curious to see what it would say. What does this mean? That's the perfect example, Jack. Thank you. Right? Now this is impressive. And this is impressive, right? That this search result gives it as well. However, I'm old. I'm like 41. I remember back in like 1990 something, if I put in this, I would get like, recipes or something back when like internet search was simple and terrible. Google has been using not learning models like this, but other kinds of machine learning that aren't quite as sort of magical and black boxy for decades. But they've also had decades to just manually tweak and refine stuff and add stuff to their code base. So somewhere in there, when the search engine is looking up Sixers, there's someone added some line of code where there's like a list of possible meanings, and one might include basketball, right? Or when the AI or the search engine is looking up the word cooked, there's a list of possible meanings, and one is cooking food, and the other is, exactly like we see here. The AI is like, oh, I think they don't mean cooked this way, they mean it that way. And again, that's a combination of manual effort, training data, and refinement of the model. I just want to emphasize how much manual effort goes into this, because you need to classify all of this data and you need to tweak the model a ton. And this is why, like billions of dollars get spent so that when we type my Sixers get cooked into ChatGPT or the internet, it knows what it means. Learning models and the math behind it is incredible, but that is not what's given us my Sixers are cooked. What's given us my Sixers are cooked is like billions of dollars and human work and time and effort. But then we do get to bundle it up into a piece of software, which is easy to share, which is amazing. Yeah, great question, Chase. Great question. What else are people curious about? Okay, cool. I have one more thing to share with folks, and then I think we can take a break. And then when we come back, we can look at code. And I will probably just throw up the code for the multi-classification model shortly before the break too, because the good news is it's very similar. But the last thing I do want to mention is multi-class versus multi-label. There's two different ways to do multi-classification. Multi-class versus multi-label. Multi-class, an image is a cat or tree or dog. A sentence is hateful or threatening, right? If we're using that that terrible example, or offensive, So multi-class is our the model can only assign the data to one kind of thing, to one class. And that's sort of a probably not the best description of it in language, but the counterexample I think will make it clear. Multi-label, an image has a cat and a tree. A sentence is hateful and threatening. The model can apply multiple labels to the data. Right? So to go back to our image, all the way from day one, this is multi-class. Right? I'm saying this is a picture of a cloud or a tree or a cat. But if I might have a picture that is indeed both, now I've got, and my cat kind of lost its ears and its terrible tail there. But now I've got multi-label. And do folks have questions around multi-class versus multi-label? And does that make sense?
I guess pay attention to the keywords or for multi-class and for multi-label would probably be a
Yeah,
help. Hmm.
exactly. And it's something we choose upfront when we're designing, the model. Like we would either build one or another. Um, so it's not like it's not like a trick we have to watch out for. It's I can build two different kinds of machines, right? Like, and the simplest example here is really um multi-class, right? I get to pick one and that's it. My duck is either Huey, Dewey, or Louie. I can build a model like this, or I can build a model like this. Right? And again, we get to decide that when we're designing and building our model. Today, we're going to focus on multi-class. It's simpler, as you can imagine, because you just have to figure out one. But these are the two kinds of multi-classification that can happen. Does that help break it down a bit more, Jason, as well? Awesome. All right, let's take a break, and then when we come back, we will write some code and build our model. So it's 9:47, so why don't we just take 13 and I'll see you all on the hour? Sound good? Perfect. All right, great discussion, folks. I think you're going to be excited to see that the code is very similar to what we've been doing. Have a good break, and I'll see everyone on the hour. And let's stop the recording. All right, so we've talked about binary versus multi-classification models, and I've got our binary model code here on the left. And we'll kind of compare the two in just a minute. Just to review, both models take in a whole bunch of different features as input, right? Both models give us probabilities that some sample or row of data belongs to some label. The difference is that binary classification just gives us one probability if a sample is or isn't something. Multi-classification will give a list of probabilities. And Jason, I think I misunderstood what you were saying before, and you're totally right that a great way to remember the difference between multi-class and multi-label is or versus and, where there's two kinds of multi-classification. Multi-class, meaning it's a cloud or a tree or a cat. Multi-label can have both, right? It could be a cloud or a tree or a cat, but it could be a picture of a tree and a cat. And so multi-label can be and, but multi-class has to be or. And you're totally right that that's a great way to remember it. I didn't, it took me a minute for my brain to catch up with what you were saying there. So thank you.
Yeah, I mean, I liked your examples of the multiple choice versus like, checkbox. I think that helped clarify it as well.
Okay, awesome. I'm glad that was helpful as well. And yeah, both are exactly the same because a radio button where you can only choose one, that's or logic right there. And then the checkbox is multiple. When we get to React, we'll get to have fun with dealing with that, but that's for another day. Um, let's take a look at these two models in code and we can see how similar they are. And let's see if I can't get them. There we go. Almost exactly lined up. We'll just, you know what, actually, we'll do that so that I can line them exactly up. So note how creating all the different layers is almost the same. The difference is right here on line 15 with the activation function. For the binary classification model, we use sigmoid. For multi-classification, we use Softmax. And actually, here's a great, I should have shown this diagram before when we were talking about this, but just to emphasize the nature of multi-classification, where this activation layer here isn't just one neuron outputting one thing. As we've been discussing, it's going to actually, well, my apologies, we'll get here in a minute. It's going to output a probability for each of the different things. So that one we'll come to in just a moment. I got myself confused a bit there. But this is actually, that is kind of what Softmax does. And so that's why we have to change from sigmoid to Softmax, because I need to end up with something that looks like this. Oh, one, where each of these might represent the probability that I'm looking at a cat or a tree. So the sigmoid gave us just one value between 0 and 1. Softmax is going to give us a number of values, one for each possible class, each different kind of label that I think can be, and they all have to add up to 1. And this is for multi-class classification. And now we can kind of, I think, go to our diagram and look at this to compare. And if the images are getting too squeezed, let me know. In fact, I'll just get rid of the binary one because we were familiar with it, and we can give this one a bit more room. So now we've got it really nice and big. So we kind of see the parts that we're used to, right? Features, the samples, the data that comes in is going to work the same way. It's got to go into our input layer. That's going to work the same way. All the various hidden layers are here in this particular diagram, just for simplicity. There's not the big ovals. We just kind of see the number of neurons where we're looking at. These are really the output neurons for each layer, right? Where we've got maybe, what is it, like 9 here. I think it's 14, and then it shrinks down to less and less and less. And then we see here in our activation layer with Softmax, what Softmax ends up doing is giving us a percentage for each possible category or class that our thing could fall into. Like if it were looking at, again, a tree, a cat, a dog, or a cloud. And I just want to check in and see if folks have questions about Softmax. Okay, awesome. Um, and I'm pretty sure I need to import my ReLU. I'll fix that in a minute when we get there. If we run into that bug, someone just remind me. So that's really the only big difference between the model part of the binary and the multi-classification model is using softmax instead of ReLU, which is great because that's an easy change. There are some other changes that we'll have to make. We'll see it when we pre-process our data. The labels for training and evaluation data are not going to be floats. They're going to end up being integers because we're going to use a different loss function. Right? And I'm not going to try and explain like how this cross entropy loss function is really different than the one we were using before, BCE loss for binary classification, because I would struggle. It accepts integer labels. It's meant for multi-class classification. And just to kind of remind ourselves of what a loss function is, let's go back to, let's see here, maybe it's our training the model. I think actually it's probably the building the model one that has the image I want to show. My apologies. There we go. Sorry about that. So the loss function's job is to figure out how wrong we were, right? And then that gets used for back propagation for the model to learn. But the loss function's job is to give us the difference between the model's prediction and the real answer, both when we're training the model and then when we're evaluating how well we trained it. And we kind of get these loss graphs where we could see like how well our model performs for different configurations. So we need to use a different loss function for multi-classification. All right, let's start writing some code. And I think let's just give ourselves a little white space because this is just gonna hide out here in the corner. And we can just kind of focus on the code. Okay. So we have to bring in our training data. And I also do want to make that red squiggly over here with F go away. F is not defined. And I think I just have to do a quick import here. From the neural net library, we were importing this class functional and giving it an alias. And let's see, maybe and there we go. So from that torch.neural net library, we're going to import the functional class as F. let's go ahead and let's take care of our data preprocessing. And let me show you all the data that we're going to be working with. So this is a new data set. It's of student performance. Can everyone, don't worry about the number values, but can you all read the top row? Okay, cool. And so what we have here is the student ID, their age, their gender, their ethnicity, their parents' educational level, how much time each week they spend studying, how many absences they've had to date, if they're doing tutoring or not, some number representing a level of parental support, some number representing a level of extracurricular engagement, some number representing a level of engagement with sports, with music, with volunteering, what their GPA to date is, and what we want to calculate, our label, is the grade they're going to get in a class. Like based on all this information, and we're not even worrying about if it's math or science, which I think just shows the limits of these kinds of tools. It's like a physics class versus an English class. There's a bit of a big difference there. But we can probably come up with some sort of generalized prediction. And so here we see this is the student ID. This student is 17 years old. Let's say 1 represents male and 0 represents female. We have ethnicity, numbers representing all these other values, a very long GPA value. And then we see here this final number for the grade in the class 1 through 4. And somewhere in here is a 0 as well. And think like A, B, C, and let's say F. So that each of these numbers is a different grade. And let me go ahead and clear the annotator. And let's add a code block here. Markdown block here. So we've got student data. And in fact, I'm just going to copy that whole thing. Let's just paste it in so we can remind ourselves what we're looking at. And the label is grade class. And the possible grades A, B, C, D, and F. So there probably is like a 5 hiding around there. Oh no, I see how it goes. That makes more sense. I got a little confused. And do folks have any questions sort of about this data and how it's organized before we start doing our pre-processing?
I guess I would say, I guess just in real world, you could probably just look at maybe a few of those. Like if you had their cumulative GPA, that's probably the best predictor of the attributes as far as how they're going to do.
Yeah, one would think, right? And we're using this data for learning. I was poking around this data before, and there were some things that caught my eye so I'm not sure how real this data is. Like over here, this student has a GPA of 3 point something, but their class predictor is like of their grade is pretty low grade. Um, In
Is
fact,
that like freshman, sophomore, junior, senior?
I'm sorry?
Is that more like their grade class, like if they're a freshman or a sophomore or a junior or a senior?
N I don't think so. I think this is because this is our label, and that's normally what you see with this stuff is like the label values at the end. I think this is the actual grade in the class that we're hoping for the student to get. But let's see here. Let me make sure that I am not confusing myself. Um, yeah, no, I don't think it's freshman, sophomore, junior, senior. Um, I do wonder if it does seem like the higher GPAs get the lower values.
On Kaggle, it says 0 is an A and 4 is an
Yeah,
F.
that's what I was. Yeah, okay. I was wondering, I was looking at this. That makes sense. Thank you so much. Actually, if you could drop in the Kaggle link, that I think that would be really good for folks. Because I was poking around Kaggle actually, because I wasn't sure where we got the CSV file from, and I wasn't sure I found the right spot. So, important point. There's like one other thing we'll have to keep an eye out for in this data as well, but that's more straightforward. So this makes a lot more sense now. Though I'm not sure I necessarily agree with whoever came up with that way of organizing the data, though it's quite possible there's a good reason for it.
Should we still go one? Should we still go 0, 1, 2, 3, 4 then?
Oh yeah, thank you. That's just a typo on my part. Thank you, Jason. 1, 2, 3, 4. Perfect. Yeah, and Stephanie, I think it was. Thank you very much for calling that because that makes way more sense. And now if we look at this, we see things that are more sensible, where the higher GPA is indeed associated with the higher grade. Because Jason, like you were saying, a GPA you'd think would be a pretty good predictor, um, past performance, kind of predicting future performance for something like this. So there is one column here, and this is not getting into the question of like, do we care about study time or age or gender or ethnicity or parental education levels? Because the context here is like sort of sociology of education and all these things. We'll always kind of look at those factors to kind of figure out correlations. This is more of like a sort of technical question of there is one column here that's not going to do us any good at all in terms of number crunching and at figuring out how well this student will do in the class. Any thoughts as to which column that might be?
I would think age and gender would be irrelevant or less relevant.
Possibly. Again, that's I think more a question for like the sociologists in terms of like how useful they are in predicting things. Um, I was looking at student ID, and I didn't mean for this to be a trick question. And so I apologize if the way I phrased it was, right? We have this student ID column here because someone probably just spat this out from the database. But obviously, you know, we can have a discussion around if age and gender are relevant or not. Student ID obviously is not. Like, we don't want to feed that into our model. So we know that we have to drop the student ID column during data preprocessing. Does that make sense? And do folks have any questions around that?
Yeah. I guess you could make arguments for every other one, but you can't make any argument for student ID being having any correlation, as far as
Yeah,
what the grade's going to be.
yeah, totally. All this other stuff, there absolutely are discussions to be had around this, but these are all, things that people discuss and consider when they're doing studies around this. but this is like purely like record tracking information that doesn't represent anything meaningful about our student. And this is a pretty real world example. Like real world data is always messy. So it's always important to kind of look it over, and we'll probably have to clean up data like this. So we know that we got to get rid of the student ID column. ID has no meaningful info in this context. Drop it. All right. So let's start our pre-processing. I'm just going to go ahead and start importing all the different things we'll need. We're going to need from that sklearn library our scalar. And can someone remind me, what does standard scalar do? More or less, not like the dirty details, but at a high level.
Reduces the numbers between, so they're between 0 and 1. Is that
Yeah,
right?
exactly. It normalizes and standardizes our data. And what does this train test split method do that we're importing as well here?
Doesn't it, like split the data into like training features and test features or targets or whatever?
Yeah, exactly. It takes all of our data, the features and labels, and it breaks up a bunch of it into for trading and saves some for testing. And it also does some nice randomization and things along the way. We know we're going to need to use pandas. And from torch.utils.data, import data loader and tensor data set. And can someone remind me, what do these guys do? Data loader and tensor data set. Like high level, without worrying about the details. Well, we'll see when we use them, and we'll come back to it then. And then pandas obviously is what we use to get the CSV data and lets us manipulate it and do all these nice things to it. So now that I've got my data, I want to grab my labels and grab my features. And I do want to make the labels into an integer. And can someone tell me for the features, how do I get rid of the labels from that data? And I guess I kind of gave it away, but
You need to do like dot drop and then put um as a like string the name of like the column you want to drop.
yep,
And then I think there's one more thing.
Axis.
Yeah.
yep, that's what I forgot the other day. Right. And what axis one does is it tells it, hey, pandas, we want to drop this whole column. I want you to drop everything along this axis, the whole column. And I want to drop the student IDs as well. So let's do features.drop. And let me make sure I get the name right. And I can do this another way. I think Chase, someone was trying to help me with this when I was struggling with this last week. I think if we just do columns equals student ID, it will do the same thing as above, but in one line, which would be nice. And let's print out features to see how we're doing here and to make sure I don't have any typos. So this looks pretty good, except
Wait, aren't you overriding the variable features?
I am because I want to get rid of the student ID column from it.
I'm sorry, I'm sorry to go back, but could you re-explain access again? Like, what if
Yeah,
access was zero? I guess I'm still trying to understand it.
yeah, totally. And in fact, I think we have a good example of it here because this columns thing didn't do what I want. Let's actually try this. Yeah, that's a great question, Jason. Uh, no, let me so I'm not sure if this will even run. Yeah, it doesn't run. So let's see what happens if we do axis equals 2. It's also an error. Yeah,
I
so I
believe
can't
one is
quite
column and zero is row, right?
say that again.
One's column and zero is row, I believe.
Oh, I thought it was like column 1, column 2. It's like, got it. Okay, that makes sense.
Okay, so you're specifying whether to drop a row or a column when you say
Yes,
access.
yes.
Yeah, yeah, Morty, good call. Good call. Thank you. Right. And so then we've got 1 is column, and then I guess 0 is row. My terrible drawing here. But yeah, we're telling pandas grade class is a column, go find it and drop it. Because especially with nested lists, maybe the data ends up getting organized differently. And we want to drop a row.
Could
So
you show us what that looks like with the zero in there?
uh yes. Oh yeah, because I was trying 2 before. That's a good call. Let's see. Yeah, so we get an error.
Well, it's because it would identify it by a number, a number of the row, if you had access as zero, since
Yeah,
we're using a column, we're throwing column in there.
yeah, I think the issue here is pandas like knows grade class is a column name. So I can't.
Try putting a
uh,
number in there instead for a row, like row number 1.
Yeah. Yeah, because I would name like an individual row.
So df.drop open 1 comma axis equals 0.
Zero. Yeah.
Oh, I see what you're saying. I see what you're saying. Good call.
And there it goes.
Yeah, good
We
call.
got
Thank you.
it.
There we go. If we change it to 1, oh, it doesn't. Interesting.
Probably because your data has headers. If you didn't have headers, then maybe it would work that way.
Yeah, yeah, I agree. I agree. Yeah, it's Pandas is a little tricky here because you have to. It's not a sort of a consistent interface in terms of how we use it. Um, but yeah, and then yeah, there was a great example to change this 0 and like if we drop just row like 2 or something like that, we can watch that happen. Where if we look over here, we've got 0, 1, and then it skips over to 3. Right? These are the student. Oh, this is pandas generated. It looks like values like row 1, row 0, row 1, and then row 3. And I would have thought that doing this by itself would be sufficient. Oh, and it looks like it is actually. If we just say columns grade class, then it seems like that grade class column is now gone. If I look over here.
Well, then you could probably throw a student ID in there as well and get rid of both at the same time.
Yep. Yep. That's a great call. And I think what got me confused before was the pandas generated IDs over here. I was looking at those when I was trying something else. So I'm going to do it in the column order so I don't lose my mind. Yeah, good call, Jason. And there we go, in one line, which is much nicer. And I'll make a note so other programmers know why we're doing this. Drop label and drop irrelevant student ID so it doesn't pollute the feature data.
Yeah, so I assume the DF drop would also have like a rows equals, you could throw probably row values in there, if you're looking to drop rows.
Yep,
That's what I would assume.
I would think so. If we just do like features drop uh looks like features equals df drop. No, maybe it's because with columns it's going by name and we would use the slicing mechanism to drop rows. That might be why it doesn't have an analog to columns.
Yeah, that makes sense.
Yeah, but that's a good thought though. And I would have thought the same thing. All right, so we've gone ahead, we've dropped that data that we don't need. Let's go ahead and do our scaling. And we're going to just make a scalar. And we'll say scale data. I'll put print features here sort of for people who want to review it later, but comment it out. Um, and we'll do a fit and transform. My apologies for typo there on our features. And let's print that out real quick just to make sure it looks like something sensible, which it does. And now let's chunk up our training and testing data, right? We've got features and we've got labels, but I need to shuffle it. So we need to create training, evaluation, data groups. So I need my training features. I need my testing or evaluation features. I need my training labels and my testing or evaluation labels. And we'll pass in our scaled features. We'll pass in our labels that we got earlier. And test size. And someone remind me what test size does?
That gives you the percentage of your test split thing where it'll be like 20% of it is going to the test and the 80% of it is going to the training.
Yeah, exactly. Thank you, Jack. And then what is random underscore state doing?
Doesn't that shuffle it 42 times?
Yeah, exactly. That's doing our shuffling so that just in case, because if all maybe someone sorted this data that they gave to us because they were using it for a report at work, but the order of that data might screw up our model because maybe all the students that do really well are at the top and they don't end up in the evaluation data. And so now we've got our data scaled, and now we need to turn it all into answers. into tensors and make ready to load into PyTorch. And this is where that data loader class comes into play. Oh, and excuse me, I'm missing a step here. We got to make the tensor before we load it into PyTorch. And we should probably make some training features.
So at this point, we're still using floating values as opposed to ints.
Correct. In just a moment with the labels, we're going to see the ints come into play. And sorry, I got myself totally confused there with variable names for a minute. Now that I have this training feature data, I'm gonna keep the same variable name, but just turn it into a tensor. And so then this should look correct as well. Yep. And the feature data we want to keep as floats because the neural net and the neurons for all the weights and biases definitely needs floats for that number crunching. But then, like you were saying, Jason, for multi classification, our label data needs to be long, which is an integer type, not float. And so now our training labels we're going to make to longs. And we're going to use this to numpy method. And we're going to set the data type to torch.long. And so this, I think we were using a view before to do this, but this makes sure we gets the data in the shape that we need it, basically. And then we do set the data type here to long. And let's go ahead and just print this out real quick. So let's just do like, we can run this with testing L. We see it looking good. Let's print training L as well. Let's print both of our feature sets as well for training and testing. And this is driving me mad because I have this variable name wrong. And everything seems to be printing out. It looks like I do have an error on line 21, probably from a typo, which is why print statements are your friend. So let's see what I got wrong here. Name torch is not defined.
Did you import it?
You know, sometimes what I've learned is sometimes it's easier just to rewrite the line because torch is defined just fine everywhere else. So rather than try and figure out the typo, I have some good guide code here. Right. It probably would have taken me longer to try and find my typo. Um, Interesting. So maybe I didn't import torch. And maybe what we're seeing here is scaled features being printed out. No, that works. Okay. I thought I had imported Torch in a previous code cell, and I could have sworn I did. But no harm, no foul. Torch is imported. I didn't have any typos. And I was also getting confused because I had a previous print statement here that we were seeing that I thought was our good data. But now we have all this stuff working. Let's comment this out and get rid of that terrible case that happened. And now we get our data ready for PyTorch with the tensor dataset method, right? And this is so that PyTorch can batch up our data and loop through it. And as you guys can tell, I make tons of typos all the time. I just, well, I type fast, but also I use like autocomplete and keyboard shortcuts and stuff because my job isn't to spell things right, and I'm more than happy to have the computer do as much of the work as I can get it to do for that kind of stuff. I would encourage everyone to really leverage like the autocomplete that your editor gives you as well. And here's where we set the batch size. And actually here, we also do more shuffling. Yeah, and let me look over this to make sure this looks right. We got a training data set, we get a testing data set. Let's run it, make sure there's no errors. I think we're looking good. Let's go ahead and let's actually train this model. Any questions on this part of our code before I move on, just to check in with folks? And other than torch.long for multi-classification, all of this is exactly the same, right, that we've been doing thus far. So the model has already been built. So let's start training it. I'm going to need a loss function. And an optimizer for the training loop. And this is different. We're using a different loss function for multi-classification. And just to very quickly kind of touch on the two loss functions. So what we were using was BCE loss for binary classification. It would output a number between 0 and 1 as a probability. Here we're getting more of a raw output score because the probability gets calculated later. Also, our label data is always an integer, which I'm not sure if this is right for BCE loss, but the main thing here is that when we're doing multi-classification, we have to use cross entropy loss instead of BCE loss to calculate a good loss function. And our optimizer is going to be the same. We're going to use the atom function. It would help if I make the model. I don't think I actually did that. And I probably need to import Optim as well. In fact, I'm going to cheat a little bit here. That's not going to help me anymore. I want to say it's from Torch, import Optim. Yeah. So the optimizer comes from PyTorch. So that's where we import it from. And now we've got our optimizer. Let me make sure the optimizer settings are what we want them to be. And that there's not something I'm missing that we have to pass in there. And indeed, I actually do have to pass in one more thing, the learning rates. And can anyone tell me what does the learning rate do? Let's give it a really small one.
Isn't it like how much it tweaks, like the weights and biases?
Yeah, exactly. Exactly. You know, if the loss function says like you need to turn east, the optimizer tell me how many steps east I take each time. Which, as you said, Chase, means tweaking the weights and biases.
But if it's too high, then you risk overfitting the data.
Yeah, I don't know if that's overfitting. We definitely, in my mind, I think of it like overshooting. Like I
Okay.
use the metaphor of like, I'm trying to like, go to Chicago, but I take such like a huge step that I step past Chicago entirely and like land on the eastern seaboard or something. If we're if we're like Superman like jumping across the country, which actually would be a nice little animation.
Okay.
Overfitting, I think of as teaching to the test. Yeah, and they sound really similar, so that's also, introduces confusion. Our training loop is going to be pretty darn similar. Um, we'll keep track of our loss rate. We'll put the model in training mode. And now we have the loop where we go through each batch. And now in here, we set the optimizer. We're going to now actually run the model with the feature data. Once we get the output for that batch, we're going to compute our loss value with the loss function. We're going to do backwards propagation using the loss function to figure out how wrong we were. And I feel like I might have a typo there, but we'll see, or a bad name. And then exactly like we were talking about, the optimizer then tweaks everything by the amount that we've set. And let's keep track of our overall loss rate. And what we can do, in fact, then is we can just calculate the average loss rate after each loop just with running loss over, I think it's the number of items in the training loader. And what this does is we can just have a nice little print statement now. And let's just say, if not, and so the very first epoch we need to skip because there is no loss rate yet. I'm honestly not sure if we need the modulo. I think that might be giving us like every 10 epochs or something like that. Um, let's run this and see how we do, mainly to make sure I don't have any typos or bugs. And then if everything is good, we can write our evaluation logic. So it looks like I do have a typo. That's an easy fix. I just need to scroll all the way up here. Maybe I need to run this. Yeah. So that's probably what happened. Um, name error, NN is not defined.
Hey, Adam, it's torch dot nn dot functional as functional. I'll do it in the chat.
Oh, thank you. Import torch NN as, yep, that makes sense. And I was running into that before and I thought that fixed it, but in fact, the issue was I had an imported torch. Import torch and then functional. I should be getting autocomplete.
It's dot functional. Dot functional.
Ah, thank you so much. That my eyes just did not want to see that. Thank you, James. So now that's good. We've made a model here. We might as well run all of our data pre-processing again, just to make sure I didn't forget to run any cell. Let's run this again. We get a different error. I'm overwriting the model from before, but who cares? This is fine. Our runtime error here says, let's see, runtime error mat1, mat2 shapes cannot be combined. So something is not in the right shape. And it looks like it's happening when I'm feeding features into the model. So I suspect up here, I may have forgotten to set something right with the shape of these things. Maybe these training labels need to have, we need to use view to change their shape or something.
Should it be features or scaled features?
It would be scaled features, and let's make sure that I used scaled features. Yep, we've got scaled features, we've got labels. So those parts are okay.
You fed features into the model down below.
Oh, you are so right. Thank you. So honestly, if I'm kind of doing a retro on this debugging session, my takeaway is with the code the way we currently have it, this is a bad idea. This is a better idea. Right? Because now it's impossible for me to make that error. And we're still getting the same.
You may have to do that view, that dot view that you were talking about as well.
Yeah, I wonder if that's what's going on here. And let me just make sure I didn't do anything silly here. Because all that should be okay. Because at this point, we don't need the non-scaled features for anything. Because we feed scaled features into here. We've already gotten our labels. Yeah, so it may be. I'm honestly a little unsure with multi-classification if we need like view one here. Let's give it a shot just with one of them, and let me print out the testing loader. Oh, that is totally in the wrong spot. It would go up here. Though the thing is, normally when we see that error, the error happens here in the data loader. So I'm a little surprised. But let's take a look at some of our labels with and without this view. Let's take a look at the data. So let's see, what else is printing here that we don't want to print? We don't want features. And now we just have this tensor. And I think indeed it is probably the view command that I missed here.
What does dot view again? What does dot view do again?
Yeah, it adds another dimension. Instead of like right now we have like one giant list. It will make instead each of these its own. It'll wrap each of these in a little list. Because right now, if we just think of this as a list, we have one row basically with 1,000 things in it, right? But with view, it would then wrap each of these in another list where it's sort of like instead of like one row with 50 things, now we have like 50 columns with one thing. And I think that is what we want to do. The multi-classification stuff does leave me wondering just a little bit about if the label data is organized with a different shape. But I think this is our error. mat1, mat2 shapes cannot be multiplied. And I think, in fact, what I'm going to do is let's actually just use ChatGPT real quick and say, for multi-classification, is this because my label data is in the wrong shape? And I don't really trust ChatGPT here entirely, but because this is a little rusty for me, I just want like sort of a second data point kind of like confirming that we're on the right path. And I think we are. So let's go up here and let's do view. And now if we print out shape one is invalid for size of, I believe, let's see if that does it. Yeah, so that didn't change stuff.
Well, I don't remember like a one and then a -1 thrown in there, but I don't know
Yeah.
what it even
Yeah,
means.
you're right. I was just pulling up the guide. I was just pulling up that lesson too to look at it. Yeah, you're totally right.
Yeah, I don't know what that means though. I'm just kind of sort of remembering it from before.
Yeah, and this is no, and this is what we're used to seeing, right? This looks more familiar. Um, okay, perfect. Yeah, I kind of let multi-classification like scare me there. I thought like, oh, we don't need this because this did catch my eye earlier. Um, but this is good to see, and it's good to debug because if nothing else, now we kind of know if we run into an error like this further down, how to go back and fix it.
Okay, so each value is wrapped in its own list.
Yeah, exactly. Right. And we need this for the labels so that because there's a corresponding row of feature data that this one needs to be related to so that PyTorch can loop through each of the labels for training and evaluation. You know what I mean? So fingers crossed. Let's see what happens when we run this. And we still get the same error, which is interesting. And also disappointing. I suspect I have a different error in my code. I think this training data set is good. We're also due for a break. So I think in like the next 30 seconds, if I can't get this sorted, I'll just move on. There's one more thing I want to try and then we'll break. And if needed, I'll fix it offline. So, yeah. Okay. I think I know what I forgot here, folks. Let's see if this does it. Yeah, I suspect I'm doing something wrong here as well. Let's take a 10-minute break. I'll fix it offline. I'll show you all the error, and this is really where we were gonna wrap up anyway, because at this point, there's really not much else that's different with multi-classification. There's one tiny change we make when we look at our model's performance, but that one's pretty straightforward. So let's take 10 and we'll see the last thing that we have on the agenda, which is evaluation. Thank you folks very much. Thanks for the help debugging as well. I'll get this one debugged offline and I'll see everyone in 10 minutes. So I kind of changed everything back because it turned out that the issue was not here at all. It also turned out that once I found the issue and also talked to like ChatGPT to get a little advice, that for multi-classification, we do indeed want our testing data, and this was me checking for nulls, which we forgot to do, but there are none in this data set. We do indeed want our labels to look like this. The training labels and the testing labels. For multi-classification, we want it to have a different shape. The error we were seeing, and let me make a change, was coming from the wrong number of input layers because we dropped student ID. And I totally forgot to remove that from here. And if we run this, and we run this, and we run this to produce our error, and I also now can give a much better explanation of this and actually point out some useful information about it. Because I jumped to conclusions here. I thought the issue was with the shape of the loader data because that was the problem that I knew. But our data was loaded in just fine, which I should have realized because in the past it was the data loader where we saw issues if those like tensors weren't shaped right. What we're looking at here is the input layer. And over here, this number 13 and this number 14, let me show you where those are coming from. Student performance. How many features do we have? We've dropped student ID. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. How many input layers, how many features do we have in the input layer of our model? 14. Because I totally forgot to modify this to get rid of student ID. So I'm sorry about that, because it was a little painful debugging live. But the silver lining is now we can actually really understand this error message. And this is PyTorch telling us, hey, these input layers, and I also, by the way, should have realized that the problem wasn't in the data pre-processing. Because again, we built those tensor data sets and whatever just fine. And our error is getting thrown here. And I got extra confused, and maybe these need to be renamed because I saw this features and I thought of the other features variable up there. But this is the features data we're getting from the training loader and running in the training loop, right? So different name. And if I was to do this differently, I might name these differently. Though some of this is, I think, the challenge of Jupyter notebooks, as awesome as they are, it does make sort of how you look at the code a little different. And so this is data that's, already in a tensor. And we're putting it into the model and it's running the model. This is where PyTorch calls that model.forward. If I can get this to let me type. There we go. Sorry, my keyboard shortcut tool is escaping me for some reason. There we go. Right, this is where model.forward gets called. I'm pretty darn sure. Like somewhere around here, I would bet, because it has to, right? Because we've made the model, we pass in the feature set, and now we're computing the loss function, which means the model's already done its work. Otherwise, we don't have an output and a loss function to calculate. So model.forward gets run. We see this error. These two shapes cannot be multiplied, 32 by 13 and 14 by 30. And if we go all the way back up to the model, what we see is the first linear layer is 14 by 30. And my guess is what we're looking at is the input neurons and the output neurons of this very first input layer. That like the 32 by 13 is the input neurons and that 14. No, because what we're looking at is expected and actual. 32, I think just maybe that's just PyTorch's number because it's a power of 2. But basically, it's trying to output 30. It's looking for 14 things and we only pass 13 in. And if I change this and we run this to correctly build the model, and just for fun, let's run all the data pre-processing again. And so just to reiterate, the testing labels are different. We don't need to do .view here. And we use this to NumPy instead of .values, which you'd used before. Thank you for mentioning that, Morty. I think they do almost the same thing. And now, fingers crossed, if we run this, we see our loss function that gets printed out every 10 epochs. And so now our model's working because we're giving it the correct number of input neurons for the features.
So to recap, the number of features is the number of features after you dropped the one column.
Exactly. Because
Okay.
it's the number of features that the data points that we feed into our model.
Okay. Yeah, because we start with 14 and then we dropped one, so that would be
Yeah.
13. So that's what
Yeah.
that's what you fed
Yeah.
in.
Exactly. And I just totally forgot, probably because I wrote the model code at the beginning of the lesson before we did the data pre-processing. And and this stuff is new to me, as well. There's definitely that, but it also just goes to show how easy it is when debugging to like get zeroed in on one path, when in fact that's not the right path. Yeah. Yeah, so that was exactly I mean, this is the best kind of problem to have because when it's an easy fix, that's great. What really sucks is when it's a difficult thing to debug, and then when you figure out what the problem is, the fix is also hard and you have to like rewrite all your code. You know what I mean? Like an hour of debugging for an easy fix is a win. What questions do people have about this now that we figured out what the problem is and kind of walked through? I'm curious what's on people's minds or things we might want to dig into a bit more.
I have a question if nobody else does.
Yeah.
Go ahead. I had one too. Sorry, go ahead.
Can you scroll back up, Adam, to
Mhm.
your binary model? I mean, your multi-class model.
Yeah. Give me a sec here. There's a lot of scrolling. There we go.
Okay. So I guess my question is maybe if we put that after the uh after the data set and data loaded, you wouldn't have to go back up there and change that.
What's
Or would
Yeah.
this be a place where would this be a time or a moment where we would be able to use squeeze and unsqueeze potentially?
That is a really good thought with squeeze and unsqueeze. I'm not sure if we could. We might be able to, but even if we could, we wouldn't want to. Because the root cause here is, and let's find one of our diagrams from this day.
Yeah, and if we can't use squeeze and unsqueeze in this scenario, then I think creating the model after the data set and data loader would probably prevent from having to from it'll prevent that from happening.
Yeah, I agree in terms of workflow, because it the error would still happen no matter like which sort of Jupyter cell order we did that in. Um, and also, um, I think I need to make a tweak in the curriculum. Because I think there is an issue in there, and to be honest, I should have run through this code a bit more. So there's a couple kind of, if we're like really root causing here, there's a couple different issues. One is a tweak in the curriculum. One is, I'll run through code before the lesson, but every time it's always the code that I'm like, oh, I know this code. I don't need to run through it. That ends up getting me whenever I'm preparing to teach. And that totally happened here today. Um, we'll just put this one up here. Um, so, moving this whole Jupyter notebook cell further down would help in terms of workflow and spotting the error, but it wouldn't have any impact on the error itself. And so then the reason why like we don't want to use unsqueeze is we've got one. So I'm going to use pH as an example because this is what I have in the diagram. If we look at our actual data, right? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And over here, I've got 1, 2, 3, 4, 5, 6, 7, 8. I better add a ninth neuron. Well, in fact, we can demo the problem with just these 8. Because the problem was, each of these inputs goes to a neuron in the input layer. And then from here, every neuron gets fed to like every other neuron. And let me do this with the draw tool because the arrow tool sometimes gets a little too clever. Right? Each of these goes to 1. And now we don't have 1 for turbidity. And so James, as to your point, like this input sort of tensor, if we unsqueezed it, I always forget if unsqueeze adds or removes a layer. But whatever unsqueeze does, we don't really want to like combine turbidity with other stuff. What we really want is we want, a neuron for every feature. So that input layer really needs an extra neuron so that for that particular data feature, it's got somewhere to go. You're absolutely right. Like in a different situation, I think we could use squeeze or unsqueeze to address this. But from my limited understanding of learning models, we really want the input layer to have the same number of neurons as our features that we feed it. Yeah, that is a great thought, though. I didn't even think about squeeze or unsqueeze. What other questions do folks have, or what else are people curious about?
I think I was just getting ahead of probably where you were going, but in terms of those loss values that were spit out, when it says like 1.2, 1.3 running decimal, what that means. But I think you were probably getting to that anyway.
Oh, yeah, totally. And let me how's this? Can everyone read this okay?
Yeah, I'm just talking about the output at the very end.
Yep.
Hmm.
So if we go down here and we look at this, so we're printing this out right here. This is just sort of like some extra code to basically what we're doing is like we run all of our batches in this inner for loop. And like, we get the loss function for each batch, which is how far off we were. And what we're doing is we're just adding it all together. So if the loss value for the first batch was 0.5, running loss is 0.5. If it was like 0.7 for the second one, we'd do 0.5 plus 0.7 to get 1.2. When we exit this loop, when we're done with the epoch, excuse me, we just take that value, divide it by the number of batches to get the average. And then we're printing that out so we can see here like the average loss. And what this line does is only prints it out every 10 epochs, so we don't just have tons of stuff printed. Now, I think lower loss value is better. And in fact, we start here at 1.29. And after all these epochs, we end at 1.1. So we've gotten losses how far we are from where we want to be, right? So we're closer to our goal after like 200 of these epochs. Does that help answer your question a bit, Jason?
So what would a perfect would you want what 1.0 then be the optimal? I guess
Even more.
what would no loss be in other words as far as
0.
okay, 0. Okay, so we're trying to reduce like a higher number to a lower number, 0 being like perfect.
Yeah, exactly. Exactly. And like if I run this again, PyTorch remembers what we did before. And we see we got even lower there for a bit. Now we're at 1.09. If I do another 200 epochs, oh, you know what? PyTorch is not remembering. Okay. This is another good gotcha, folks. I did not do this on purpose, but because I have the let's create our PyTorch model in the same Jupyter block where I'm running this, every time I'm hitting run, it's creating a new model. So in fact, nothing is getting remembered. So we're gonna just put this here. We actually did it up where we made the model, so I'll just leave it there. And now what should happen is when I run this again, and remember that unless we like reset the Jupyter notebook, the model still exists and still keeps track of everything. So for our next 200 epochs, we're starting from here with the weights and biases and everything here already set. And this is what tensors get us, because tensors kind of remember all their changes. And now we see our loss function is getting lower, right? So it takes a lot of epochs, right? Just to get a percent. But it's getting lower, and the model's getting better and better and better and better. And in fact, I'll run this like one more time, and then we'll do our evaluation where we can see that now that the model has been trained, right, we can now evaluate it.
One last thing, sorry, and
Yes.
then I'll.
Yeah,
Okay,
absolutely.
so as far as zero being like the model's perfect, what would the worst number be? Would it be two, or what would
Oh,
it be?
in this case, I don't think there's an upper limit.
Okay.
It's not like with labels where it's like 0, 1, 2, 3, 4.
Hmm.
I think it's just if you think about that loss graph that I was making with all this stuff, I think this can just go as high. It can be as bad as we want.
Okay. Okay.
Yeah, that's a really good question though, because for all these other things, these numbers are within certain bounds. So I'm pretty sure on that one. Let me go ahead and do our evaluation code because there is one change here, and I do want to show that. And then let me also show you, I actually do have, well, one, possibly two assignments, though they're a little rough around the edges, but I think they'll be fun for the afternoon. So let's do our evaluation. So we need to import from this torch metrics library. We need to import the accuracy class. And I'm going to create a new instance of this accuracy class. And unlike with binary classification, we need to tell it your task is to evaluate accuracy for multi-classification. And note here that multi-label, like we were talking about before, cat and dog and tree, if would count here as well. For student grades, this makes sense for building a multi-classification model. And it's kind of nice we get the auto sort of type helping completion. And we also have to tell it how many different kinds of answers can there be. And our lists of possible answers are A, B, C, D, F. And Stephanie, thank you again for figuring this out. That translates to 0, 1, 2, 3, and 4. So there's 5 classes, right? These values, as to your point, Jason, like these are our labels. Like a 0 is an A, a 1 is a B, a 2 is a C, and so on. We have to set the model into eval mode. Can anyone remind me what one of the most important things that eval mode does is? So eval mode does a couple things, but one of the big ones is it turns off drop-offs, right? Because we don't want neurons to drop out for evaluation. For training, that's good. It's like running with weights on or something, and then you take them off. Like if it's in one of those like Dragon Ball Z anime or something. Like Goku's training with his weights, but then or in like 10,000 times gravity, and then when he goes to fight the villain, he doesn't wear the weights. Which I'm assuming most people are familiar with Dragon Ball Z, and if not, I think get the reference as well. Though Pokemon I know is sort of the more universal. Eval will also make just the code a little more efficient. We don't have to keep track of certain things. We don't have to do a gradient descent because we don't have to calculate loss. And now we grab our testing loader that has our testing data, not our training data. And this helps prevent overfitting. And we pass in those features and we've got our output. And this is where multi-classification is a little different. Let's see what this one argument does. The dimension to reduce. Yep. And I'll explain what this line of code does in just a moment. And now if we run this sucker, I'll have a typo first of all. We see that we have relatively decent accuracy. If we run this a couple more times, I'm curious how much better the accuracy gets if we run this one more time. I think this is giving us I think we want the accuracy to go down, but I honestly need to double check. Let's actually just ask. This is, I think, a great ChatGPT question. Okay, so indeed yeah, so I think a higher accuracy value is actually what we want here, which is interesting because I ran the training and it dropped a tiny bit. But let's see how we do again. And now it went up a tiny amount. So here, for accuracy, higher is better. Like 0.87 represents 87% accuracy.
When you run those trainings again, is that cumulative or is it just redoing it?
It is cumulative. Yeah, as long as I don't, because Jupyter Notebook keeps track of everything in memory. If I was just running Python code, then, if we ran this program again, it would not be cumulative. But Jupyter Notebook is holding the model that we created, which is, let me go all the way up. This model that we did on line 28, Jupyter Notebook is holding this object in memory. And what a PyTorch model does is, as long as it exists, it keeps track of the whole history of all the training runs and all that stuff. And in fact, the error that I had a little earlier was I did this because I just wanted to have it be there as a reminder. But I forgot that what that meant is every time I hit this replay button, we're making a brand new model, in which case, since this gets overridden each time, the old model's lost. If I, in Jupyter Notebooks, restart the server, that would obviously clear memory. If I do run all, that would run all the cells, including the one that makes the model, which would clear memory as well. But in this case, because the model is still there in memory, which is a Jupyter Notebook thing, this is cumulative. And
Thank you.
yeah, great question. And with PyTorch, there's undoubtedly a way where even with Python code for us to somehow like save the model, because that's how these things are used in the real world, where like you train it, and you keep working on it. And I don't know if PyTorch does that by like exporting. Probably there's probably some file format or something like that that saves the model configuration, which would be an interesting thing to look up. And now, in fact, we've gone up to 86% accuracy. So this is the difference between multi and binary classification evaluation. We need to condense the probabilities for each possible class. And really here, condense is the wrong word. We need to get the highest probability from all the probabilities. Because over here, let's print out, let's see, torch.max of output data. I'm not sure how clean this is going to be, but let's print out this output data. And let's maybe, yeah, actually, this is good. So it's kind of hard to tell because of the format of these numbers. And we're seeing like things like raised to like the -27th, and my PyTorch skills aren't quite enough to know the right way to convert this. Like, I don't know if I can do values, so I'm not even going to try. But what we see here is all these rows, but there's 1, 2, 3, 4, 5 columns, right? And so this value represents the probability of an A. This value represents the probability of a B. This value, the probability of a C. This one of a D. This one of an F, right? Or in whatever order the model is giving it to us. And so for multi-classification, we get the probability for each possible class. And what the max does here is it returns the maximum value because we want the highest probability. Because that's the model's best guess. Because this is not multi-label, I can't have an A and an F at the same time, right? We might be able to have an image that has a cat and a dog in it, but I can only get one grade. So I want the highest value, and that's the model's prediction as to my grade. So that's the key difference here in terms of how the prediction data is outputted by the model and then how we evaluate it. And that's really just a one-line change, but it is conceptually important. And I just want to check in and see if folks have any questions around that.
I do kind of think as far as the accuracy rate, there's a higher correlation, between the features that we're, using to predict, kids' grades, what their grade's going to be. As far as being, water, it's kind of hard to tell the correlation between the attributes, but
Yeah.
it seems like for grades, correlation's a lot easier to see.
Yeah, we're actually get to see our model get better here, which is nice. You touch on a really good point though, Jason. Like I was going on Kaggle, and I'll just show you all. Kaggle for this water potability data set, because you guys made some good points, and someone posted here that they think this is a fake data set because each feature has perfectly normal distribution. You talked about that sort of like normal curve, where this is like the most. This would be, if everyone the average grade is supposed to be a C, though these days with grade inflation, it's not. But in a perfect world, the idea of a grading curve is that, you tweak how it's graded, with the idea being that the average class score should be a C, right? So that we're measured relatively to each other. But so this person is saying that this water data like looks too good to be true. Also, that there don't seem to be correlations between the features that you would expect, which, as someone who I don't know anything about water, so you do have to have some domain knowledge here. So as to your point, just because our model is getting better doesn't mean that we don't know the provenance of this data. Like I actually, Stephanie, if you can share the link, that would be great. But our data could be totally fake, for example, right? So you always really have to think about your data and where does it come from? Because you could train an amazing model, but if you train it on crappy data, then out in the real world, it won't be a lot of good. But for our purposes, for learning, this is 1,000% better because it does help us learn the techniques for making a good model, right? Even if we have bad data, that doesn't stop us from learning the skills to make a good model, which is really our focus. And I agree with you. It's nice to see the accuracy going up. What other questions do folks have? What else is on people's minds? Okay, so I actually do have an assignment which I'd like to propose to folks. So I did a little digging, and let's see here, where can I find it? There it is. So on Kaggle, speaking of data, there is a stellar classification data set that is multi-classification data, as in you can have different kinds of stars. So this is like 1,000 observations from different telescopes and stuff. There's frankly a whole lot of features. There's 18 of them. I have no idea what most of these things are. The data is real. It appears to be from a good source. It's under the public domain. And if we take a look at it, we can kind of see what we're looking at. If I can just scroll over enough, and then I think our label is, because that's what I want to show everyone, is the label value. Here, if we just download it, we can open it up and we can take a look. Sometimes they just want to make it really complicated. But anyway, while that's getting open, so I can show it to you all. What I was thinking is this could be some cool real world data to try to do a multi-classification model on. Now, I have no idea how accurate our model will be, but it's different data, it's real. There's also some good discussion and some good notebooks, though, to be honest, these go well beyond what we've covered. But there is some really cool stuff going on here in these notebooks. And here we can see this person in their Jupyter notebook did something like very similar to what we've done. They do some data analysis and stuff. And I think it was maybe this notebook. There was another notebook that had a really good breakdown of stuff. And so it'd be kind of cool. Like you can kind of look through to see what someone else has done. and they talk about the data set. This is where it gets a bit more advanced because they're like people who know about stars and stuff like that. Um, and if we get into where they start doing, like they do all this data analysis, which is a huge part of this stuff in the real world that's kind of out of scope for us. And they're using, frankly, they're using like more sophisticated machine learning approaches that I don't know a lot about, that is beyond scope. So I don't think there's a notebook here, unfortunately, that we could like choose as a good guide. But if you all are comfortable just taking a crack at like making a really simple multi-classification model with the understanding that it's probably going to suck, then this could be a really cool data set to do it with. And we have like a pretty good discussion around this and some other examples. And the star classification data, we can look at it here in a spreadsheet where it'll be a bit easier to see. I'm actually, there we go. It must be this class column that is our label, right? Where we see star, galaxy, quasar. So just, playing with this data, like we want to get rid of object ID. You might have to convert each of these to a number like 0, 1, 2, 3. Because in its current form, it's probably not going to work. Could be really cool. And I realize that's a bit open-ended. So it might be good to do as a group or individually, but I did want to throw it out there as a possibility. There is also, I think, this someone put together a really good tutorial on multi-class classification for images over a data set of images that's from Stanford University that's sort of a standard for image training. It could be really cool to like read along with this and sort of code along. Now, a lot of this is like what we learned, getting the training data, splitting the test data. They do some graphing here, which we didn't really get into, and it could be cool to just sort of copy that and do it. Here, though, in the training, they go well beyond what we learned in class with a number of different techniques. They're doing things like they are getting like RGB data out of pixels and stuff. Frankly, they're doing some stuff that I don't really know what this does. That's probably specific to like image manipulation and machine learning for images. Data loaders we're familiar with, right? We saw that. But then with the model, this gets way more sophisticated, where again, they're using a different kind of model, they're using different features, they're using different optimizers. So I don't know if it's realistic to code along with this, but I do think they've laid this out really well and with image classification. And I just wanted to show this to folks as well. And I'll share both of these links. And it does, we are working on making better assignments. At the same time, as you can see here, like as soon as you step outside of the realm of sort of like tutorial data, there adds a lot more complexity, which is again because ours is really like an overview course. We're only spending 6 days focusing on this, and it is an exciting but complex subject. So let me stop the recording, and then we can kind of decide what we want to do for the afternoon.